Okay, Assalamualaikum and very good day. So we just finished part 1 and part 2 in the previous video, which is we already talked about the flow rate of the flow and continuity equation. So continue with the part 3, which is about Bernoulli's equation. So in this part 3, we will learn deeply about how can we use the Bernoulli's equation for the application of the flow system in a pipe or tubing. Okay. Expected that after you complete this part, you will be able to apply the Bernoulli's equation, which is might be useful to determine the condition of the flow in a fluid system. So basically, okay, the derivation of the Bernoulli's equation is actually derived from the combination of energy which is involved in the fluid system inside a pipe or tube. Okay, so the first energy that should be considered in the Bernoulli's equation is due to the potential energy. Okay, so what does it cause? How this potential energy occur? Okay, so basically the potential energy is considered or is caused by the elevation of the fluid. Okay, so that's why in the equation here is considered the Z here, which is represent the elevation of the pipe, okay, or of the fluid from the reference point, okay. And the second energy which is involved is actually the kinetic energy. Oh yeah, by the way, the W here is actually stand for weight, okay, and the Z here is actually the elevation, okay. And as I mentioned just now, the kinetic energy. When we talk about the kinetics, kinetic represent a movement. Okay, so the kinetic energy here is actually due to the velocity, the movement of the liquid or fluid. Okay, so that's why if you look at the equation here, which is used for a kinetic energy, it involves the v, which is velocity. Okay, because it has the movement, so that's why it has the kinetic energy. Okay. And the next one is actually flow energy. So what does it mean by flow energy? So flow energy is actually consider the amount of work, okay, to move the fluid, okay, from a certain point, okay, and actually how we consider how much is energy needed, okay, to move the liquid when it faces a certain amount of pressure. Okay, so that's why in the equation here, there are terms of pressure inside the equation. And basically, Bernoulli's equation is actually derived by the summation of all of this energy, which is flow energy, okay, potential energy, and kinetic energy. So the total energy involved inside the system here is actually represents by this equation, and this is the equation that been used for Bernoulli's equation. Okay, so now if we look at the diagram here, okay, so for example, we intended to move fluids from section 1 to section 2, okay, so for example, this is a point 1 or section 1, and this is the section 2, okay, so if we intended to move this liquid between these two different points, okay, so what are the energy involved here, okay, so in this case, we assume that there is no energy is being removed or added into the system. So if we assume that, okay, which means that energy at point 1 will be equal to energy at point 2. Okay, so therefore, the total energy that we already derived in the previous slide, if you still remember, the total energy equation which is involved in a fluid system, which is due to the energy, due to the flow work energy, and due to the potential energy, and this one is due to the kinetic energy. So the summation of the total energy at point 1 and the summation of total energy at point 2 should be equal. Okay, so this is For example, this is the equation 1. Okay, since all the terms here contain W, which is weight, and if we divide all the terms in this equation 1 with W, so the equation become like this. Okay, this is the newly derived equation after we divide with W. Okay, so this is the equation that we call Bernoulli's equation, okay, which is consider all of the energy involved in the fluid flow system. Okay, so if you look at this Bernoulli's equation, okay, between point 1 and point 2 here, because it's noted as 1 and 2 here, okay. So each of the terms involved in the equation here is actually represent the different kind of energy possessed by the liquid or by the fluid in the system, okay. So for example, the term 1 here, which is a P1 divided by Y, which is a specific weight, is actually represents the um, flow energy per unit of weight, and this one is actually represent the energy due to the potential energy, okay, divided by weight as well, and this one is actually represent uh, the kinetic energy. Okay, so the term 1 usually called as pressure head, and the term 2 is actually called as the elevation head, and the last term, okay, which is this one, the term 3, is also known as the velocity head. Okay, so it's got its name by the parameters which is on the top here, which is pressure, z, which is elevation, and velocity is this one. Okay, and all of this is considered as total head. Okay, so therefore for we can summarize that the Bernoulli's equation is actually consider the change in elevation head, okay, which is z1 here, okay, and pressure head, okay, which is the term P1 divided by Y, and also the velocity head between 2 points in a fluid flow system, which is the velocity head here. Okay, so even though there are many application of Bernoulli's equation, however, okay, there are some limitation about the Bernoulli's equation. Okay, so the first limitation is the Bernoulli's equation only valid for incompressible fluid because the Y, or specific weight of the liquid, is assumed should be assumed same between 2 points. Okay, so you cannot have the variation of specific weight between the point 1 and point 2. Okay, so that's why it's only valid for incompressible fluids. Okay, and the second limitation of the Bernoulli's equation, it cannot have any additional any mechanical devices between 2 points. Okay, so for example, you want to use the Bernoulli's equation between point 1 and point 2. Okay, so in between point 1 and point 2, you cannot use any mechanical devices such as pump or compressor, which is can remove energy or add energy in a system. Okay, there should be again point number 2, it cannot be used when there is mechanical devices which to add it between the 2 point. Okay, why it cannot use the mechanical device? Because the equation, okay, states that the total energy in the fluid should be constant. Okay, because we have limitation by knowing that the basic concept inside this is the total energy between point 1 should be equal to point 2. So if we want to use this theory, okay, there cannot be any mechanical device between this point 1 and point 2. Okay, and the third point is there should be no heat transfer throughout uh, this fluid. Okay, so for example, you cannot put any heat exchanger between these 2 points. Okay, and lastly, there should be no energy loss due to the friction. Okay, so for example, the pipe used the surface is not smooth. Okay, so it causes lots of friction. Okay, so when there is a friction, there will be energy loss uh, throughout the journey to reach point 2, okay, from point 1. Okay, so there should be no friction occur, okay, in a system. Okay, so here I will list down the general procedure that you need to do if you want to apply the Bernoulli's equation inside the flow system. Okay, so the first one is you should decide first, okay, which items are known and you need to be found. Okay, so for example, the question is about the movement of liquid from from point 1 to point 2. Okay, so based on the equation, you should identify first what's the information that you need to get. Okay, so for example, maybe the equation wants you to get the velocity at point 1, for example, or the question wants you to get the z2. Okay, so you have to identify what is the unknown info that you need to determine in the question. Okay, and the second procedure is you need to decide which two section is in the system that you will use to apply with the Bernoulli equation. Okay, so for example, if you are choosing this one as a point 1 and this one is the point 2, okay, there should be information, okay, provided for each point. There might be some point which is not given based on the question here, but the info at least should be available between the 2 points. Even though you not been provided with the full info, but some of info is provided so that you can use the Bernoulli's equation to get the parameters requested in the first step. Okay, and the third procedure is you should write the Bernoulli's equation from left to the right. Okay, so for example, in this case, okay, maybe I put a point 1 uh, on the left and point 2 on the right. Okay, because maybe the movement of the liquid from lower part to the higher part. And the fourth thing is you should know where is your reference point. So therefore, it is very important for you to sketch the diagram. Okay, so every time you got equation related to Bernoulli's equation, you have to sketch the diagram and you have to identify which one is considered as the reference point. Okay, and the next step is you should simplify the equation from the information provided. Okay, so for example, there might be parameters which is you can remove because it's become zero value, or maybe is equal on the both sides, so you can just cancel out. Okay, and lastly, you can just solve the problem by using the algebraically and get the desired term which is you already identify in step 1. Okay. Well, you can't really understand about this Bernoulli's equation until you try to do a problem related to Bernoulli's equation. So let's try this example. Okay. So for example, in the figure shown below, okay, there is a water at temperature 10 degrees C is flowing from section 1 to section 2. So that means the water flowing from point 1 to point 2. Okay, so at point 1, which is D1 is the diameter is 25 millimeter, and the pressure gauge here is 345 kilopascal, and the velocity at point 1 also given here, which is 3 meter per second. Okay, meanwhile for section 2, the diameter of the pipe at point 2 is given, which is 50 millimeter. Okay, and it is 2 meter above section 1. Okay, so that's mean location, it is related about Z. Okay, so Z2 actually greater than Z1 for 2 meter. Okay, so I will define this thoroughly for this part in the next slide. Okay, so by assuming that there is no energy losses in the system, you need to calculate what is P2. Okay, so assumption here in which that there is no energy losses here, which means that it can use the Bernoulli's equation in which that it assume E1 will be equal to E2. So therefore, you can use Bernoulli equation in this case to solve what is P2. Okay. So let's take a look at the solution. So as usual, what is the first thing that you should do? Okay, so the first thing is you should sketch the diagram with the complete info which is provided in the equation. Okay, so for example here from the equation I managed to extract the information as I showed in the previous slide before, in which that D1, P1 and V1 provided for point number 1. Meanwhile for point number 2, you only have D2. Oh yeah, this one is it is wrong. As I mentioned just now, Z2 is greater than Z1 at 2 meter, which means that it is actually Z2 minus Z1 equals to 2 meter. Okay. And the next step is you should list down all the info. Okay, this is the most important things. Okay, so when you want to list down all the info here, you should segregate it between two different points. Okay, because when you want to substitute into the equation, okay, it will make you easier and it won't minimize the error. Okay, because if you note it wrongly, you will use the wrong parameters. Okay, so that's why here I segregate between the information at point 1 and information at point 2. Okay, so at point 1 the diameter P1 and V1 provided here. Okay, and at point 2 you only have information about the D2 and Z2 minus Z1, but the info about the P2 and V2 you don't have it. Okay, and in fact this is the info that you need to determine based on the question. Okay, so now let's take a look how can you use the Bernoulli's equation to solve the problem. Okay, so you definitely know that you have to use this Bernoulli's equation, and the question asks you to determine what is the P2. Okay, but however, if you check all the information provided in the question, which is I already listed in the input section in previous slide. Okay, so you don't have the V2. Okay, and of course you don't have the P2. This is the information that you need to get. Okay, but however you have another parameters which is not given in the equation, which is V2. Okay, and for Z2 and Z1, even though it didn't provide directly, but you do have the information of Z2 minus Z1. So at least this which is equals to 2. So at least this correlation you can use in this equation. Okay, so how about V2? Okay, because before you can determine the P2, you have to determine first the V2. Now let's take a look. Okay, okay, so before we proceed with the V2, how can we calculate the V2? You have to get the Y, the specific weight, and G value first, G value. Okay, so actually this value you can get it from the table or appendix. Okay, because in the equation is already stated that the water at temperature 10 degrees C. Okay, so therefore by using the appendix, Okay, I can't remember the table number, but I think it's table A something. Okay, so you can get the information here in which that at that temperature the specific weight for water is 9.81, and the, okay, this one is the wrong unit, and the G is 9.81 as well. Okay, so done with the left side. So now move to the right side. So in order to get the V2, actually you can use this supporting equation. Okay, if you still remember what is this equation. Okay, so we cover this in the part 1 and part 2, in which that this is actually continuity equation. So we need this continuity equation to get the V2, because from this continuity equation we know that the flow rate Q1 will be equal to Q2. Okay, and the A2, of course, you can get it by using this formula, okay, because the D2 is provided. Okay, same goes to A1, in which that you will manage to calculate the A1 because D1 is provided in the question. Okay, so by solving this equation, oh yeah, the V1 is provided as well from the equation. So lastly, you will get what is V2. So once you get the V2, you can substitute equation. Okay, and this is the output. Okay, what I mean output here is after I substitute all the information inside the formula. So if you notice that from the output on the left side here, I will find first what are the Y and G value, which is I got from the table. Okay, and the A1, okay, which is I use for the continuity equation here. A2 for the continuity equation to calculate the V2. So once I got the V2, I will use the V2 to substitute into the Bernoulli's equation. Then I will manage to get my P2 is 329 kilopascal. Oh yeah, remember that the Z1 and Z2 is actually can be combined here. So this term Z2 minus Z1 is actually 2. Okay, so this is my final answer, which is 329.59 kilopascal. Okay. Okay, so in Bernoulli's equation, there are some case which is called as a special condition, okay, in which that it occurs at tank or reservoir and nozzle which exposed to atmosphere. Okay, so let's take a look at this diagram. Okay, so there are 2 points, which is point A. There are 2 points which is exposed to atmosphere. Okay, which is point A and point F here, in which that these 2 points didn't have any solid barriers which is confined the area here. Okay, so therefore at these 2 points, actually the pressure at these 2 points, because it is at most it is exposed to atmosphere, so we consider pressure at point A is equal to 0, and so do for point F. Pressure at point F, okay, the P at point F is equals to 0 as well, because it is exposed to atmosphere. Okay, so what happened when the pressure at this 2 point is 0? So if we look back with the Bernoulli's equation for the total heat variables or parameters here, okay, it does give effect through this equation, because P1 terms here will be 0. Okay, not just that, okay, in fact the velocity here, the VA, okay, the VA will be equals to 0. Why the VA becomes 0? Okay, because the VA is actually derived by Q equals to VA. So if we want to get A here is actually area and A here is actually the point A. Okay, so I should just write that if let's say this one is V1. Okay, so this one is V1. Okay, V1 will be assumed equals to 0. Okay, so because this area is it has a large surface area, so if we want to calculate the V, which is equals to um, Q over A, okay, the value here will be nearly 0 because the A is bigger, okay, it has a large surface, so that's mean the V will become very small. So that's why we just assume that when it is exposed to atmosphere, okay, the PA here will be 0, and in fact the PF here will be 0 as well because it is exposed to atmosphere for the pressure. Meanwhile, for V at point A, VA here will also consider as 0. Okay, so therefore this term, the P1 and V1, and in fact if we consider this is as a point 2, the P2 will also can be eliminated or cancelled from this equation because the value is 0. Alright, so now let's do example for the Bernoulli's equation in a special case in which that point which is exposed to atmosphere. Okay, so the equation shows that there is a siphon, okay, which as shown in the figure above here, which is used to draw a water from a swimming pool here. Okay, so the pipe that makes up the siphon is actually has a diameter 40 millimeter. Okay, so this is actually the siphon. Okay, and with the pipe here is 40 millimeter. Okay, and and it terminates with 25 millimeter diameter of nozzle. Okay, so actually the pipe here is being reduced the diameter upon the end of here, so that's why it reduced to 25 millimeter at the opening point here. Okay, exposed point here. Okay, so assuming that there are no energy losses in the system, calculate the uh, volume of flow rate through the siphon and pressure at point B, C, D, and E. Okay, so as a summary, we can say that, okay, this siphon is being used to remove water inside the swimming pool here. Okay, so the siphon used here is actually has the diameter at the beginning is 40 millimeter, and throughout the end here, which is near to nozzle point, the diameter reduced to 25 millimeter. Okay, so as you know that the PA will be equals to 0 and pressure at F here will also equals to 0, and you need to get what is the flow rate through the siphon and the pressure at a few difference point, which is pressure at point B, pressure at point C, pressure at point D, and pressure at point E here. Okay, so here I write it down again. What is the information that you need to get? Okay, so you need to get the Q and P for these 4 different points. Okay, QB, QC, QD, and QE, and also same as the pressure, you also need to get the pressure at each point, which is B, C, D, and E. Okay, so let's take a look. How can you solve this problem? So as usual, the first thing that you should do is sketch the diagram and list the information. Okay, so let's begin with the sketch the diagram first, because that before we can list the information, we need to identify any point in which that we can cancel out. Okay, so from the diagram here, okay, as this is the special case in which that a few points, there are 2 points which is exposed to the atmosphere. Okay, so we have to identify first which point is it. Okay, so it shows there are 2 points, which is point A and point F, which is exposed to atmosphere. Okay, so therefore at point A here, okay, we can assume PA is equals to 0 because it is exposed to atmosphere, and same as PF here because it is at the end of the nozzle here and it is exposed to atmosphere. So we can assume PF equals to 0. Okay, and next thing is about VA. Okay, so VA here we can assume equals to 0 because that the area here is big. So in order if we find the Q equals to VA, and if we want to find the V here, okay, it's become V equals to Q over A. So as the area here is bigger, so therefore the velocity will be smaller. So that's why we assume V at this point is 0. However, the VF here, we cannot assume 0. But just put that you don't know about the VF. Okay? That's why I put equation marks here. Okay? And other thing is about the properties. Okay, in this question it didn't provide the condition of the solution, I mean the temperature of the water, okay, or temperature of the liquid here. Okay, so if this information is not provided, okay, so the information the common information which is we need in the Bernoulli's equation such as G and specific weight for water, we can just assume that the value is 9.81 or 9.805. Okay. Okay, so since from the sketch that we draw in the previous slide, okay, so we can get some information about the few parameters that you can cancel out. By the way, this is the information that you need to determine from the question, okay, in which that you need to get the QB, QC, QD, and QE, and as well as the pressure at these 4 points, PB, PC, PD, and PE. Okay, so from the identification of the point, exposed point, which is at point A and point F, okay, so we can cancel out few terms from the Bernoulli's equation. Okay, so this is the Bernoulli's equation for this question, in which that I label as point A and point F. Okay, so we know that for point A, we can cancel out the PA, which is equals to 0, and as well as the VA, which is equals to 0. Okay, this is on the left side or on the A side. Okay, meanwhile for point F, okay, we can only cancel the terms of PF. Okay, and by the way, from this equation, actually you can get what is the VF. So how can we use the VF in order for us to calculate all of this information? Okay, so since this is a correlation between A and F, so that means we can get, it can help us to get any of the parameters at the upper point here. Okay, so here is the information that you can extract from the diagram just now. Okay, so we know that the dA, we just assume it's 0 because it is too big. Okay, so PA is equals to 0 and VA equals to 0. Meanwhile, for point F, okay, we already have the information of diameter at point F, which is the nozzle diameter, which is 0.025 meter, and PF is equals to 0. Okay, and velocity at point F, we need to calculate it, and the ZA minus ZF is given, which is 3 meter. Okay, so from this VF information, okay, we can actually get the QF. Okay, so if we substitute this VF into the VF for the Q here, the volume flow rate, okay, we manage to get the QF. Okay, and in order to calculate the QF, you also need the information of AF here, so that you will be able to calculate the QF. Okay, however, we didn't manage yet to get the information required here. Okay, so let's take a look in the next slide. How can we relate the QF with other Q at the which is needed by the equation here. So here I just show to you what is the how can I get the VF and QF, which is I substitute into the equation. Okay, and this is the info that I just got from the table, which is even though it's not given in the equation. So in the equation, so we just assume that this is the value that you're going to use. Okay, so we need to get the QF from this formula. So since that AF can be get from this formula, and the DF is given, of course. Okay, and there we are, we get the QF, which is equals to 0.0036 3766. Okay, so in the previous part, we done with point F, which is we able to determine the QF. Okay, so now we proceed with point B, in which that we will determine the QB and PB. Okay, so we know that we have to use Bernoulli equation since we want to determine information for point B. Okay, so we need to correlate between point A and point B. Okay, so if we compare between point A and point B, okay, as usual, point A, we can still cancel out the PA and VA. However, for PB, we cannot cancel it because PB is not exposed to atmosphere. Okay. But at the end, our target is we should get the VB first, because from VB we can get the QB, which is QB equals to VB times AB. Okay, and this is the input that we can get. Okay, so we know that DA, we just assume it is 0. That's why the VA becomes 0. Okay, and for point B, we know that the diameter for point B is actually 0.04 because it is located somewhere in the middle. Okay, and from VB, as I said just now, we can use it to determine the QB. Okay, and AB we can just calculate it by using the diameter provided at point B. Okay, which is given in the diagram. Okay, which is 0.04. Okay, so how can we get the VB? Okay, this is where we will relate the point F and point B, in which that by using the concept of continuity, okay, we know that the QF will be equals to QB. Okay, so therefore, okay, we will get the VB from the QF, which is equals to QB. Okay, in this case. Okay, so by dividing between Q divide by AB, in which that the area, actually there are two methods. Either you can calculate the AB by using this equation, or other method is you can get it from the appendix J, but the value is not different very much. Okay, so for example, if I just calculate manually, I will get this answer 0.00126. Okay, however, if I just refer to the table, which is table J, okay, for SI unit, I will get the area straightforward, which is 1.257 times 10 to the power of minus 3. Okay, it's not much difference. So it's up to you which value that you want to get. Okay, so as you already have the VB, so that you can substitute into the equation, the Bernoulli equation that I showed in the previous slide before, in order to calculate the PB. Okay, so VB from here, okay, and the Y, the specific weight, is also given, or we get it from the table, which is we assume that it is at 9.81. Okay, same goes to the G, we also use 9.81. Okay, so we already have the value, then we substitute it, and finally we get the PB value here. Okay, So the QF, sorry, the QB is actually, we determined it already in the first part, which is equals to QF. In this case, it is at 0.0036, sorry, 3766. Okay. So from this one, as a conclusion, we managed to get what is the PB and the QB. Okay, we're done with point F and point B. Now we proceed with the point C, which is you need to get what is the QC and PC. Okay, it's the same procedure as we did before, in which that the first thing is you have to sketch and list down the information. Okay, so first of all, we know that you have to use between A and C. Okay, and PA equals to 0 and VA equals to 0. Okay, of course, you have to determine the VC first. Okay, and this is the information from the info before. This is the input about the point A, and this is the info about point C. Okay, and here, as it is noted here, okay, ZA minus ZC, okay, ZA minus ZC will be negative value because C in this case is higher than A. Okay, so that's why the value here is negative. Okay, if you want to refer again, you have to go to the diagram which I showed in the earlier part. Okay, you can have a look at the location of between point C and point A. Again, because point C is higher than point A, so that's why the value is negative. Okay, and once you got the VC, you can use the VC and substitute into this equation in order to calculate the volume flow rate. And again, the AC you just can determine from this equation AC by substitute the value of DC here, okay, in which that the DC here is given in the diagram. And the same procedure as we did for QC, in which that you also will equating between QC with the QF because of the concept of continuity, okay, in a system. Okay, and again, you can determine the AC by using this formula, or you can just get the value of AC based on the given diameter information. So you can just get the AC directly. Okay, and then you just substitute the value. Okay, so since the value of the ZA minus ZF, which is negative, okay, have a look at this information in the input, which is in the slide before. Okay, and just multiply with the Y, the specific weight, and then substitute the VC information. Okay, so at the end you manage to get the PC, which is in this case is negative value minus, sorry, it is minus 16.2627 kPa. Okay, so we're done with the point C, which is at the end we already get the information of QC and the PC. Okay, so for point D, and if you need to determine the value of QD and PD, pressure at D and flow rate at D, okay, you have to use the same procedure as we did in point D. Because the point B and point D is at the same level and it has the same diameter. Or in other words, we will say that the QD will be equals to QB. Okay, and the same as the PD will be equals to PB. Okay, so have a look again with the location. Okay, so point B is same level as point D. Therefore, the PB will be equals to PD. And of course, the Q will be the same throughout the system because it used the concept of continuity equation. Okay? Okay, so just now we already covered about the Bernoulli's equation, which involve in a special case in which that when the certain point is exposed to atmosphere. Okay, so we finished that part already. Okay, so now we cover on the special case in which that a special condition in which that Bernoulli's equation we use it in the Venturi meter and other closed system in which that we don't know the velocity, or other words the velocity is unknown. Okay, so let's take a look how can we solve it. Okay, but this time I will straightly give you examples so that it will be easier for you to understand the concept. Okay, so this is the example of Bernoulli's equation in which that for a Venturi meter and other closed system with unknown velocities. Okay, so if you look at this diagram, this is shows the Venturi meter in a closed system. Okay, the equation stated that the Venturi meter shown in the figure is actually carries the water at 60 degrees C. So by the way, this is the water which is flow at 60 degrees C. Okay, and the specific gravity of the gauge fluid in the manometer is 1.25. Okay, so the SG of the fluid which is used in the manometer here, okay, is actually 1.25. Okay, and you need to calculate what is the velocity of flow at section A, which is VA at this point. Okay, and the volume flow rate of water at A, which is QA. Okay, so how can we solve this problem? Let's take a look. Okay, so as usual, you have to sketch the diagram and try to get information from the diagram as much as possible to be this down in the input. Okay, so first you have to identify available info and related point in Venturi meter. So we know that we have to find the VA and QA, which is located as this point. So A is located as this point. Okay. So which point that we need to relate? Okay. So I think the information available only on the point B. Okay. So in fact, at point B, we don't really have much info. We only have the elevation info between point A and point B, which is the distance here is 0.46. Okay. However, the distance between this level and the liquid which is used in manometer is not available, which means that the Y here is not available. Okay, we only have the distance between B and A. We don't have the information between the level at A here and the liquid for Venturi meter. Sorry, the liquid for manometer here. Okay, the label as Y. Okay, so from that we can list down the info. Okay, so as we're gonna use the point A definitely. Okay, because we need the information of VA. Okay, and the SG here is actually the SG for the liquid in manometer. Okay, and in fact the pressure at A also is not available, and we have the information about the diameter at A, which is 0.3 meter. Okay. Meanwhile, at B, we do have the diameter here, which is the inside diameter of, sorry, where's the cursor gone? The inside diameter for B is 200 millimeter. Okay, here. So that's why the dB here is 0.2 meter. And again, the info for PB is not available and VB is not available as well. But we do have the information of the distance between ZA and ZB, in which that ZA minus ZB is 0.46 meter. But in this case, we put it as negative because A is lower than B. Okay, so that's why it's become negative 0.46. Usual, we'll do the equation plan or mind mapping for the equation that you need to use to complete this problem. Okay, so we know that definitely we need to use the Bernoulli's equation. Well, this is the Bernoulli's equation in which that you need to determine the VA in which on the left side terms. Okay, so we will use the correlation between point A and point B. Okay, since this is the only information available in the equation. Okay, so this is the main equation that we will use. But this Bernoulli equation, actually we can rewrite it to make it simple in order to incorporate with another equation. Okay, so from this equation, we bring the PB on the right side here to the left side. Okay, and we combine it with the PA, since this is the term which is the same on the bottom part. Okay, so that's why PA minus PB divided by Y, the specific weight. And also the ZA, we bring the ZB on the left side because we already have the information about the ZA and ZB, which is minus 0.46. Okay, and the terms of velocity, we bring it to the right side. Okay, so from this equation, okay, we still not managed to solve the equation because we don't have information about this term, and so do about this term we don't have the complete information. Okay, so what we can do is actually we can combine it with the equation by using the Venturi concept, or this is actually the manometer concept. Okay, so if you look at this derivation of the equation, actually I derived this equation by considering the pressure device measuring. Okay, so this is actually the manometer. So remember that in order to use the manometer, we have to divide the section in the manometer, the U-tube section, into a left and the right section. Okay, and we will find the level which has the same level on the both side. Okay, so this is the level that I intend to use. Okay, let's say this one is a level P and level Q. Okay, so definitely the level here is the same, so pressure at P will be equals to pressure at Q. So what are the terms which is contribute on the pressure at P, which is pressure on the left? Okay, so if you look at this point, okay, pressure at P is actually contributed by pressure A, okay, which is this one. Okay, pressure at this point, okay, plus with Y times YW. Okay, this is a specific weight. Okay, so if you look at this term, there are actually two different types of liquid being used in a system. First is YW, which is refer to the specific weight of the water. And the second one is YG, which is the specific weight of the liquid which is used inside the manometer here. Okay, so actually this one you will use YG, which is Y gauge. Okay, which means it used in the gauge. Okay, and Y water here. Okay, because there's a water inside this region. Okay, so on the left side, we know that it's contributed by PA plus the length here, Y, okay, times with the YW, okay, and plus with 1.18. Okay, this is the distance that we consider 1.18. Okay, because still here is still a water, so that's why we times with the water here. Or otherwise you can also rewrite this equation like this: YW y plus 1.18. Okay, is similar. Okay, and what about pressure which is contribute on the point Q? Okay, so for point Q, the pressure is actually contributed by the pressure at B here. Okay, pressure at B plus with the elevation here, which is 0.46, okay, times with the Y water, specific weight of the water, because here still consists of water, and plus with the Y times YW. Okay, this is the area that we are talking about. Okay, so we notice that actually these two terms available on the left on the right side, which is good, in which that we can cancel out at the end. Okay, and plus with the y.18 times with yg. So this is the area that we are talking about, which is on the right side. Okay, so that's why it multiply with the yg, because here it consists of liquid in manometer. Okay, so this is the equation that we derive from the manometer concept, okay, but the Venturi concept. Okay, so actually the YG here, we can get it by using the information of specific gravity which is given in the equation. So in this case, the specific gravity given in the equation is actually 1.25. So we know that the specific gravity is actually a ratio of the specific weight of the liquid, okay, Y specific of the liquid in this case, divide by a specific weight of the water at 40 degrees C, which is YW. And YW is actually, the value is 9.81. Okay, so why we're going to use this equation? So if you notice that in this equation, we have few terms which is needed in this equation too. Okay, so if you notice that it consists of PA and PB. Okay, so if we rearrange this equation, okay, we will use this term in order to replace the terms in here. Okay, so therefore we can solve this term, okay, and we already have this value, the ZA minus ZB, and the only info or the only terms that we don't have the information yet is the term on the right side here, which is about the velocity. Well, for the terms of related with the velocity, we can use the continuity equation. Okay, so I will show you later on how can I use this continuity equation to replace or to complete the terms on the right side. Okay. Okay, so we know that we have to use this Bernoulli equation to solve the VA. Okay, so in this case, actually, we can use another supporting equation. Okay, which is we will use two supporting equation. Okay, so for example, in this equation, this term, which is term 1, we can solve it by using the Venturi concept or equation that we derive from the manometer sides. Okay, and for this side, which is term 2, okay, we solve it by using the continuity equation, in which that we get the derivation VB equals to 2.25 VA. Okay, so now let's take a look at how can we use the equation of manometer to solve terms number 1. Okay, so since both of the part which is left and right part consists of y times yw, so we just cancel out these two terms. Okay, and then if we rewrite again the equation into this form, okay, and then we can cancel out the yw here, okay, but we divide it again with yw here. Oh yeah, by the way, this one is actually yw because it shows that the liquid in the system is actually water. So here you divide with the specific of water, okay. It's become like this, okay. And for YG, definitely we can get it by using the information of SG, which is provided in the question, in which that we know that SG, which is 1.25, is actually the ratio of YG divided by Y, a specific weight of water at 4 degrees C. And this one, the value is 9.81. Okay, so at the end you will get that what is the YG, which is 12.25 something. Okay, another thing is you have to be careful with this YW here, in which that it refers to the specific of the weight in the system, not at 4 degrees C. So according to the question, the YW, okay, here is should be refer for the y what of the water at temperature 6 degrees C. So the specific weight of the water at 60 degrees C is actually 9.65. It's not 9.81 because this one is we only use it to get the YG because it used at standard condition, which is 4 degrees C. Okay, so I hope that you clear about that. Okay, so this one we just solve it, and at the end we get the parameters is become like this: PA minus PB divided by YW equals to 0.78, in which that later on we will use this value to substitute into this equation, okay, which is 0.78 now plus with the minus 0.46 equals to all of this term, which is term number 2, in which that you can simplify this whole term into VA parameters. Okay, but you have to work out again what is the value of VA here by substitute this term into the VB. Okay, I will explain in detail in the next slide. Okay, so the final step is we just need to substitute all the value that we get by rearrange or rewrite the equation. Okay, so remember that we still have to use this Bernoulli equation, and we have to replace all of these term, the term here, the first term, and the second term here, okay, with another supporting equation, in which that this one is from the continuity equation and this one from the correlation of the manometer. Okay, and this one is actually given, which is negative 0.46, right? So the term for question, the second term we already get from the continuity equation, in which that we know that VB is 2.25 VA. So since the term here need for you to put it this way, so VB here is actually 5.06 VA. So we can replace the VB to the power of power of 2 in here into these terms. Okay. Meanwhile, for term here, which is the first term here, we got it from the manometer equation, okay, manometer relation, okay. So we derived it already in the previous step, in this step, in which that the first term is equals to 0.78, okay. So we just substitute all the value, okay, as same like this one, okay. So at the end we managed to get what is the VA value. Okay, so we solved the question in which that it asks you to determine what is the VA. velocity at point A. And the question also asks you to determine what is the QA. Okay, so in order to determine the QA, we just have to multiply between the VA and AA. And from the previous procedure, we know that the AA is actually equals to 7.069 meter square, and you just need to multiply with the VA that we get from here, which is 1.24, okay, meter per second. So finally, we will get the QA value, which is at 8.77 times 10 to the power of minus 2 meter cube per second as a volume flow rate. Okay, so that's it. Thank you. And this is the output that I calculate using the Excel. Maybe you can use it as a guideline. Just want to double check your calculation parts. Okay, so here it shows that the value of QA and VA that I got from the calculation. Okay. Thank you very much. We finished part Bernoulli's equation. Okay, we look forward to see you in the next part, which is part 4 for Torricelli's law. Okay, thank you.